Okay, so today we'll discuss about routing algorithms. You can hear me as well as see the slides. Please reply via audio. I won't be able to see the chats in the thing. You can see me. Means you can see the slides. Audio kekala. Right. So routing algorithms is the topic of discussion today, and we last day we discussed about autonomous systems. I gave you a small assignment, all those things. Okay, so how we are discussing routers, that is network layer. We are in network layer routing. We saw network layer addressing IPv4, we saw IPv6. We'll take up later on after this routing, unless someone takes it up as a short presentation, some student. I'll cover it. Okay, so autonomous systems, say these are different. This is the internet, and internet has different domains. You call them as autonomous systems. Within this there are some routing protocols which you call as internal routing protocols, that is open shortest path first, that is OSFP, then extended interior gateway routing protocol, EIGRP. So such things are there, and between the domains, between the autonomous systems, there are something it is called as border gateway routing protocol, BGP. So such things are there. So that's what our discussion is. Basically this is a graph, how you find the least cost. If you have taken up graph theory in your maths papers, basically it is finding out the least cost paths and least cost trees, and how different routing algorithms have different ways to compute this least cost tree. That is giving rise to different routing algorithms. Okay, so different approaches are followed by different routing algorithms to compute the least cost tree. Okay, so you will model this internet as a weighted graph. So A, B, C, D, all those things are routers. These are routers, and you have the edges, you have assigned weights. Now weights or cost. In internet the cost is not distance alone, it could be the congestion, it could be the cost, actual cost also, it could be some other parameter. Say you might have a situation where you don't want to route your internet traffic through countries, routers which are situated in not so friendly countries. So you will assign a higher cost to those routes so that they won't be taken up. That way, you won't even advertise your routes to your routers in your geographical area. Will not even sometimes advertise your routes to those countries, routers situated in those countries. Such hostilities could be there in internet. So such situations being there, each of these links, each of these edges have some cost assigned to them. So it's not just the money alone, it could be the traffic related cost, it could be the congestion, it could be the actual cost, it could be that is number of hops that could be there. But this is not the number of hops. This could be some other parameter which has been decided for this by this node, by this network. So this is the internet network of networks, that is internetwork. So so you need to find out the least cost path between a source node and a destination node. So intermediate you will have n nodes. So say for instance, to compute a path from A to G, you have different paths. Say you have a path like this, say A, B, C, D, G. You have a path like A, B, C, F, G. You have a path like A, B, E, F, G. So three paths. Among this, which will be the least cost path, that is what the calculation is. So ഇതിലെ least cost path ഏതാണ്? ഇപ്പോൾ ഇവിടെ 7, 10. So this is 6, 7, 8, 9. Then 7 plus 4, 11, 12. So I think this is the least cost path. A, B, E, F, G. that is 6 7 8 9 മറ്റേത് 10 ഉം മറ്റേത് 12 ആണ് വരുന്നത്. So this is the least cost path. Now there are static routing algorithms as well as dynamic routing algorithms. Static routing means always it will send these packets over the same path, whereas dynamic routing algorithms, they will the routing tables in the intermediate routers are periodically updated. So dynamic routing is the player in the internet. Actually that is how your internet can work properly. If you have a fixed routing thing, that is not a very good approach, but basically it's a combination. You can say it's a combination of both static as well as dynamic approaches. As earlier mentioned, some of these entries might be prefixed, that these routers are not to be traversed in any case, because they might have what do you say, you will assign the infinite cost to those routes, because that routers might be situated in a not so friendly territory, or this might be costlier, or some other reasons. So there are other agreements also. We mentioned about peering agreements. So peering agreements means suppose your Airtel wants to, Airtel and Reliance autonomous systems are there. They think that they study, that is a traffic originating from a Reliance customer, it will be carried to Airtel customer with Airtel network, and from the Airtel to the Reliance, they understand that the traffic is almost equal, so they have some sort of reciprocal arrangement. Say Reliance will say, I'll take your traffic free of cost, you take my traffic free of cost. That is peering arrangements. So peering arrangements ഉണ്ടെങ്കിൽ കോസ്റ്റ് വേറെ രീതിയിലായിരിക്കും കമ്പ്യൂട്ട് ചെയ്യുന്നത്. So some preference will be given, but there are some things. Your ISP has to ensure that your traffic through its balance is maintained. Otherwise the other person will try to charge, because he sees that this guy is sending me a lot of traffic, so why don't I charge this person? So peering relationship will break. It's usually the peering is a give and take. Peering, we discussed about this peering earlier. So peering arrangement, transit, both these we discussed about that in autonomous systems. So coming to this, if you have n routers, in this case you have seven routers here. This each of these will be considered as a root of the tree, and you will try to find out the least cost path. So here say A is considered as the root, and you will compute the least cost for A to each of these. So from A to B you require 2 hops, B to A also 2 hops. The cost should be same in both directions. That is a very significant thing, but sometimes it might be the other way around also, but this is a simplified case, but usually the cost will be same in both directions. Okay, so each of these nodes, so this is the least cost tree for A, and this is the least cost tree for B, C, D. Each of these will be considered as the root node, and then you will compute the least cost path to each of these nodes, intermediate nodes. Okay, each of these nodes in the network. So you will have, if you have n routers, you will have n-1 least cost path from each router to any other router. So that means n into n-1. So if you have 10 routers, you will have 90. So 90 least cost path for the whole network. So that so if you take the case of the whole internet, so you will have unwieldy routing tables. So basically the routing is done as a hierarchy. Each router need not know about the entire internet. That is the key principle there. It might have information about some portion of the internet. It need not have information about the n things. And then there is you have the concept of route aggregation. So that makes it work very, very efficiently. Hierarchy is the key there. Hierarchical routing is the key there. Okay, right. So different routing algorithms do exist. They are evolving, but basically the difference is that how they compute the least cost tree. the way which they least cost tree, how they compute, and also how they update the paths in case some of these links fail, how they update their routing tables. That is how the difference comes between different routing algorithms, right? Okay, so you have two, broadly you can say you have two types of routing algorithms. Some is intra-domain, that is within the autonomous system, and something which is called as inter-domain, that is among autonomous systems. So that is what you call as a path vector routing. The BGP, the border gateway protocol, is a form of path vector routing. Then intra-domain you have distance vector routing as well as link state routing. So broadly you can divide the intra-domain routing algorithms into distance vector and link state routing. So, and the examples of link state routing you can give it as routing information protocol, then OSFP, open shortest path first. So all those are the intra-domain routing algorithms, right? So inter-domain and intra-domain. So we'll first take up intra-domain routing protocols, and we'll see distance vector and link state. Then we go to path vector. That will be the approach. Border gateway is taken up at the end. So okay, this will be continuing in the subsequent sessions also. So distance vector routing. So it's an intra-domain routing protocol, and basically it is more or less like a gossip how this routing works. So when in distance vector routing, you can't say it is a gossip like that, but basically when a router whenever it has some information, it will just say at frequent intervals it will exchange whatever information it has about the network. So network in the sense it will exchange its routing tables with its neighbors. That's what each router will does this task. So and then you will do some computation. To check whether do I get new information. It's like that. So we will see an example. So so this is the strategy. Each router will periodically exchange information with its neighbors about what it knows about the network. Okay. So whenever there is a change in the network, there will be an exchange. We'll see that this has some problems, but nothing is perfect, So different strategies does exist. Say to update and build the routing table. One is called as a Bellman-Ford algorithm. Then there is a Ford-Fulkerson algorithm and a dual FSM. So this is a proprietary thing. The other two are open algorithms. This is a proprietary algorithm which is run in Cisco's networks. So so this are the examples: RIP version 1 and version 2, interior gateway routing protocol, extended interior gateway routing protocol, and there is a academic thing like Babel. Babel is a interior gateway routing protocol. So it's this could be run. You can run thing on routing protocol and see there are simulators for that. Some but you can try out say different options. So online tools are also there to see how different routing algorithms work, but for the course we won't discuss all those things, but we'll see this. So the basically in distance vector routing, say each node will, so these are the networks, and these are the intermediate routers, A, B, C, D, E, F. So these are the routers. So each of these routers will periodically exchange information about whatever it knows about the network, internet as a whole, with its neighbors. So A will exchange its information with F, B and E. B will do the same with A, B, C, right? So A and C, right? Similarly, F will exchange with A, like that. So how does the router know when it starts up? So router, as we discussed, router is a combination of both the hardware as well as software, and router has several input lines as well as output lines, input and output ports. Each of these ports have a specific address as well, physical address also, right? There is a physical address for each of these ports. Okay, so are we okay? Yes. Are we on track? Shall we move forward? All right. Okay, so I find the class very silent. That's why I asked. Okay. So, so this is the Bellman-Ford algorithm. There is nothing complexity in this. It's a minimum. ഇതിൻ്റെ മിനിമം കണ്ടുപിടിക്കുക എന്ന് മാത്രമേ ഇതിനകത്തുള്ള കാര്യമുള്ളൂ. മിനിമം കണ്ടുപിടിക്കുക എന്നുള്ളത്. So you have two nodes x and y. X and y. So x and y. You have paths through a path through node A, a path through node B, and a path through node C. So this is the general case. So you will take the minimum of this path. That will be the least cost path between these two, right? Minimum of these three paths. So sum of this. So this is the sum of xa and day. This path is xb, cxb and dby, and this is cxc and dby. So this is the cost, and this is the shortest distance. Dij is the shortest distance, and Cij is the cost between nodes, right? So this is the minimal path. So through an intermediate node, you are calculating the path between these two. Now once you have calculated a path, say dxy, you have a path. Now you want an update. You have found out a new path through z. So some intermediate node called z other than a, b, c. Then again you will take the minimum of this. So this is the cost for this path, and the distance for this path, shortest distance. So you will take the minimum ആണ് എടുക്കേണ്ടത്. അതാണ് Bellman-Ford algorithm. Basically that's what. This will run in a for loop forever. So whenever there is a change, you will take all the path weights and take the minimum. അതാണ് അതിൻ്റെ algorithm. The skeleton of this is that nutshell is that always find the minimum path. Whenever there is a change, you update the tables based on this metric, right? So that is the Bellman-Ford algorithm. Hope that is clear, right? Yes. So this, how the router will know when you power on the router, how the router will know what is the how the router will know what is the state of the router tables. Router arbitrary ആയിട്ടായിരിക്കും ഒരു ടേബിൾ ആദ്യം ഉണ്ടാക്കുക. It will just randomly have some values there. Then so it will have information probably about its own immediate neighbors, but it will send something which is called as a greeting packet. It's sort like, hello, I am router A. So it will send this info to router B, C, D, so and even other routers. So in this case, A to itself, this is the next the cost for A to communicate with itself, reach A is 0. A to A is 0 always. A to B, it sends a greeting packet and it monitors what is the cost involved, the round trip time, for instance, the delay. You can take that as a cost. Then say I get a delay of say 100 milliseconds, it's very big. So I'll say I'll assign a cost of 4. Then if I get a delay of 50 milliseconds, I'll put a cost as 2. Like that, some parameter will be there. So A says my cost to reach B is 5. B also sends a greeting packet and it says my cost to reach A is 5, right? 150 milliseconds, right? That Okay, so same way 125 milliseconds. Now anyway, similarly A to reach C, all those you will send greeting packets and get back information. Send hello and get information. To reach to reach router E is not able to directly reach to this. So initially will be infinity. Initially the distance to E is masked as infinity. Similarly for in the D's routing table, the distance, the cost to reach node D is shown as infinity. And again for C, the cost to reach B as well as D, it's B and C, it's marked as infinity because it is not able to directly reach all these routers. Okay, now once this is there, then they will start exchanging these tables. So how they update is that, so A is exchanging us say C has exchanges routing table with A, so C is giving this update to A, and it also receives updates from B as well as D. Okay, so we'll take the case of C. A is receiving a updated routing table from C. It's C's routing table. A has a routing table with it. So what it does is that, say I'll just update my routing table. Say to reach C I require 2 hops. Okay, right. I'll update it as 2 hops. To reach A, it says that I need 4 hops. Right. I'll update it as 4. Then to reach B through C, that is B through C, it says that it needs 4 plus 2, 6. That's what the 6 comes here. So 6. You'll add 2 for each. That is C where reach ചെയ്യാൻ വേണ്ടി 2 ഹോപ്പ് വേണം, 2 കോസ്റ്റ് വേണം. സോ എല്ലാ ഇതിൻ്റെ കൂടെ 2 ആഡ് ചെയ്ത് ആണ് A നേരത്തെയുള്ള it will add this information, that is to reach C വരെ എത്താൻ 2 വേണം, അപ്പോൾ B വരെ എത്താണെങ്കിൽ 6 വേണം, A വരെ എത്താൻ 2 വേണം. So to reach to A through C I'll require, even though it's a wrong way to calculate this entry, I'll say reach 4 and update it. C doesn't have any information updates about how to reach D. E reach ചെയ്യാൻ വേണ്ടി 6 വേണം, 6. So C says 6, 4 plus 2, 6. C വരെ 2, അത് കഴിഞ്ഞ് 4. Right. Now then it will compare. It won't just blindly believe that, it will compare and then update the routing table. It says that this is I have a least cost path, then why should I take this 4? It will dump that. Then again to reach B I already know it is 5. Why should I go for a highest path? 6. Other dumping is 5 updater. C, it's a new information. Right. To reach C I require 2. Right. So it will update. D വരെ എത്താൻ 3 വേണം, അതിപ്പോൾ മനസ്സിലായി. A already knows that to reach D. It will exchange this to C as well. So this information is updated. Right. So this is the way in which they update. So the routing tables are exchanged and it is updated. We will wind up in 5 more minutes. Okay. This is how you update. Each of these routing tables are updated, and whenever there could be a possibility that at some point some links might fail. എല്ലാ സമയത്തും ഇത് നെറ്റ്വർക്ക് എല്ലാ ലിങ്ക്സും ഓൺ ആവണമെന്നില്ല, ചിലത് ഫെയിലിയേഴ്സ് വരാം, റൂട്ടർ മൈറ്റ് ഗെറ്റ് have developed problems. All those things have to be updated dynamically in the network. The problem with the distance vector routing is that this is what the problem is. Any decrease in cost, that will propagate fast, but if some links fail, that is links fail means it's an infinite path. You won't be able to reach that router. That will propagate only slowly. This is what we call as count to infinity problem. Count to infinity problem എന്താണെന്ന് we'll just illustrate. So we'll illustrate with an example with a case called two-node instability. So count to infinity problem is a problem which is faced by distance vector routing algorithms. So this is two node instability. Say there are two routers A and B, and A and B, they are connected to X. They are trying to commit the path through X. So X to reach node the network A, the LAN X through A, it is 1. So B, for B to reach X through A, the cost is 2. Now what happens is that the link fails, link between X and A fails. You see that here, there is no line here, there is a line here. So after the link fails, A knows that A find out some path to reach X through some other way, and it says there is 16 is required. Then it will just say I can reach, it knows that I can reach X by what do you say, through some path which has a cost of 16 other than the direct link. Now even before it sends its routing table to B sends an update to A telling that, say you can reach, say B already knew that it is having a path of 2. But it doesn't know about this link failure. A did not update it. Before A updates, B sends an update to A telling that, see, I can reach X through with a cost, what do you say, 2. So A thinks that through B it has a least cost path. So it says I can reach B through with a cost 1 and plus this 2. So with the cost 3 I can reach router X. That's how it updates. Now after a while what happens? A will try to update B. A will try to update B. So A will try to update B means it is B, see, you can reach X through a path with a cost 3. So B thinks, say, I can reach X through A with a cost 4 because this hop is 1. So this continues until this both of them, it takes several updates, then finally you will reach it. Both of them will understand that the link is broken, it's unreachable. So after several updates, this continues. This is what we call as a two-node instability. So there are two strategies adopted. One is what we call, to prevent such a situation, one is what we call as a split horizon. Another one is reverse poisoning. Split horizon എന്ന് പറഞ്ഞാൽ say when B is sending an update to A, it will avoid the entry of A, whichever routers through which ഇപ്പോൾ ബിക്ക് എക്സിലേക്ക് റീച്ച് ചെയ്യാൻ പറ്റുന്നത് എ വഴിയാണ്. So it will avoid the entry related to A from that routing table, so that A will not get a false information. In any case the link fails, A will have the best update, right? It will just avoid the entry related to router A from its table which is exchanged to router A. That is split horizon. So it won't give the entire routing table, it will just give the truncated routing table. It will just avoid the entries which are related to A from the routing table. So that will, in that way, A will not be corrupted by a wrong information from B, right? That is split horizon. Then other way is reverse poisoning. In this case, you could say B could send an update routing table to A, even including the routing entries related to A, but with an information telling that, with a comment, for example, telling that I got this update from A, so update from you, so be careful when you use it. That is what. So if you have a latest update, follow that. If you have a better information than this, that is the best thing. This is what I know from you, so that way. So it is up to you to decide what is it, whether this is the latest information or whatever you know is the latest information. So A will be aware that, say, B is sending me a routing table, but he got the update about this link from me, but now I have the latest update about that link, so I should retain that and discard whatever B has sent me about this link, right? So these two strategies are adopted to prevent this count to infinity problem in distance vector routing. So that's what is distance vector routing. We will take up what do you say,